down depending on how fast you're moving. Your travel speed and your wire speed both create your amperage effect. Okay? So if you're doing a lot of manipulation, then yes, your current, your wire feed, and your physical speed play into role. If you were to just drag it as one steady bead, like on submerged arc welding, which we'll talk about later, that factor is variable then. And then your amperage is more consistent. But as we know with GMAW, especially short circuit, in order to get a good weld penetration, you have to have the right technique in order to use it, which creates a lot more weld manipulation, a lot more wire manipulation, and techniques within that weld puddle. Okay? Yeah, most of you that have bent welds or coupons and had them come apart, you realized how important the technique is on GMAW. All right, we're going to talk about the modes of transfer now. Number one is spray arc. Spray arc is what we have in there on the machine, booth K right next to it, the big L-Tech machine, right? Spray arc is typically only good for flat welds, groove or fillet, and then horizontal fillet only, right? So it's basically the same as a 7024 electrode, very viscous, very liquidy, but you can put down a lot of weld. In my opinion, it's an easier weld, but it is susceptible to centerline cracking due to problems, which we talk about with submerged arc later as well. However, here we do have a consumable electrode. What happens is it superheats that coming off and it just kind of sprays it in there. Any of you that have tried it by now, it took weld 3, you know it's just spraying it in there. High deposition rate, heavy weld, very good penetration, very good fusion. Don't have nearly as many issues as you do in other ones, okay? By far the hottest process in any GMAW welds, okay? What I'm going to read here will say spray transfer is considered, so I'm on page 3-11, right hand column, second paragraph, third sentence down starts out, spray transfer is considered to be the hottest, followed by pulsed arc, globular, and finally short circuiting. Therefore, spray transfer is the best for heavier sections of full penetration weld joints as long as they can be positioned in the flat position. Again, flat. So, important to keep in mind, right? Globular. Globular is kind of this, exactly what it says. It heats up, the resistance, heats up, creates a big metal droplet, just like from a faucet or a dew leaf. And then it drops down and it gets on it. As you can see, it's a wide bead, but not very deep penetrating. Okay? Versus here, spray, pretty consistent, nice deep pattern, good penetration, so forth. Okay? Pulsed arc. The welding current is variable. It's pulsed between high and low current cycles set by the welder. 15 years ago, pulsed arc machines were hard to come by. They were a pretty rare thing. Nowadays, with some of the new tape functions and the new exotic alloys that are out there, pulsed machines are not as hard to come by as they used to be. However, traditionally in most of our coursework and stuff here, it's still going to require a special type of power source, right? It's not just a straight constant voltage machine. It requires its own power source with its own capabilities, shutting things in and off, and then pulsing it back and forth between high and low current cycles and so forth. Okay, that's not to be confused with high frequency. That's a different type of machine, or a different thing. We're talking about pulsing it, so basically it's just taking it up and down. Okay. All right. Here shows an example of all 4 of them. This is the 4 modes of short circuit transfer. I apologize. Wrong spot here. I'm going to back up. The book tells us pulsed arc gas metal arc welding requires a welding power source capable of producing a pulsing direct current output which allows the welder to program the exact combination of high and low currents for improved heat control and process flexibility. Okay, that's how it talks about pulsed arc. Now we're into the short circuit transfer. Short circuit transfer results in the least amount of heating to the base metal. All right, which in certain situations, if we're welding small stuff, decorative stuff, a finished product that needs to be a nice streamlined box, right, or a fuel tank, we don't want to see a lot of distortion, we don't want to see a lot of warpage, we don't want to see a lot of heat effect in there. Okay, this might be exactly what we need. I know we talk about things like sometimes like, oh, well, it doesn't penetrate very well, it's not a very hot process. Doesn't mean that's a bad thing. Okay, not everything has to be held to a destructive bin test manner. Simple ladders, things like that, naturally they should hold, they should be good welds. But we're not going to have them in the same context that we would a bridge or a vibration or a building, okay? So depending on especially lighter gauge stuff, GMAW short circuit's the exact perfect opportunity for us to have that. We can control heat input, high wire, good weld speeds, everything else. So technically the drop begins to form, it advances towards the base metal, touches a weld puddle, and then the circuit is broken. Now this happens so fast that you can barely hear it, okay? For some of us, if you get your wire out of sync, your voltage and wire, you can hear it pretty well actually. Factors for transfer modes: number one, shielding gas, current level, voltage level, and power supply. Any of you that have welded with straight CO2 and then you switched over to 75-25, it's a tremendous difference, right? Just the environmental of inert gas itself helps create much stabler arc for a lot of things, a lot better weld quality, a lot of more maneuverability, and you can do what you want with that weld puddle at the same time. It also keeps it cooler, can have a great effect on porosity and embrittlement within that weld puddle also, by just the shielding gas alone, okay? Advantages: semi-automatic process, so the difference is stick, we said it was manual. You fed the wire 100% yourself, everything was all manipulated this way. Semi-automatic, the wire feed mechanism is the automatic stage of this. You still have to be able to move it, but at this point it's considered a semi-automatic process versus manual, okay? An automatic process might be when we get into submerged arc welding, to where the wire feed and possibly even the big roller or drum or the plate is being driven 100% by itself. In that case, it's an automatic process. You still have to set it up, but it's still an automatic process. High production rate, no slag to remove. However, again, we've talked a little bit about the silica and how it can sit on the top of the weld pattern. The weld puddle, we need to knock that 5 to 6 thou off, or whatever it might be, down to a good clean white metal, not gray metal. Okay, gray metal's typically what we call, just when we wire wheel it, we want to knock it down to that white metal so that we know that all those impurities on that top layer are gone. Okay, clean process. For the most part, much cleaner than anything else. It's a lot faster. You can weld most alloys as well. Now naturally, you get into most alloys, stainless steel, we're going to need to do a tri-gas. That's when we do get a little bit more sensitive about the gases, the speeds, the polarities as we get into different alloys here, okay? Some of the limitations: it's not exactly made for outside conditions. Very little tolerance for contamination, dirt, grease, and oil. Doesn't allow it to weld as smooth or be as flexible as, say, 60-10 or 70-18, right? You usually have to be pretty clean, very few impurities within it. It is usually limited to shop welding. The equipment is a little bit more complex, and there are consumables. Consumables is the big thing, right? Make sure you always have consumables with you. You don't have to carry a ton of them, but you have to have them there, because if they go out or something goes wrong, then you're shut down. And that's a huge part of this, is you can't afford downtime. When we want to talk about lean process and so forth else, it's always important to run somewhat lean. But the biggest problem anybody has in any production is downtime. Quite simple. The easiest thing: if we're not producing a product, we're not effective. Okay, we're not efficient. That's the easiest way to lose efficiency, is if we cannot produce a product. All right? And you would hate for something as simple as a 25-cent contact tip to shut you down for 2 hours worth of production. It may cost you $200 because of a 25-cent contact tip. All right? Now, you don't have to have 5,000 of them out there, but you need to make sure that you're watching these things, your consumables, your materials, so that you're being able to use your time wisely as we're moving through this stuff. Okay? All right, discontinuities. Those three are in everything, right? No slag. Don't produce a slag at this point. Flux core arc welding. Basically, most of you know this is most of you have done this at this point. If you haven't, then we'll be having a different conversation. Come talk to me and I'll show you the difference. Self-shielded flux core arc welding, there's no gas, okay? Basically, you've got a tubular wire. Inside of the tube is the actual flux, okay? The powdered metal, the granular powder. Wire connector, you still have a contact tube. Your material, and if you notice, it does create a solidified slag on top of this weld pool, okay? Oh, excuse me. Technically, this is what it should look like. Now, we don't run this self-shielded machine in here because it would just be another whip, and we'd have to change that out all the time as well. What we run, you can run the same, especially if you're running the same size of wire self-shielding, out of this nozzle. Typically, if I've had to do it, I usually leave the nozzle on it just to protect the contact tip, but we don't have any gas there. You can pull the nozzle off and just run the straight bare contact tip. However, it's really hot and nasty, and you will go through quite a bit of a large amount of contact tips if you're running through this type as well, okay? That's where these ones are a lot smaller. The contact tip is a really small piece. It costs a fraction of the cost of what the other ones do. And it's a little bit further away from you to where you won't get, number one, this is a heat shield for your hands, so your hands don't heat up as fast. This is typically going to be used outside where we have atmospheric air, things that are not going to see or need a lot of high quality welds. You can still make a high quality weld with this. Any of you that have been through that class, you know the difference between going downhill versus uphill on this welder, right? Or in this process. That's a huge difference. However, typically, most of your welding procedures are not going to be used running an inner shield or a self-shielded wire. It's usually gas shielded and so forth, okay? All right, so here's the difference. Electrode identification system here, E for electrode naturally, right? The number one number for flux core is your strength. So if this is a 6, it's 60,000. If it's a 7, it's 70,000. That's much different. The other ones, it was 2 numbers, right? 2 or 3. In this case, we're a flux core, we're only using the 1. There's some ESOB electrodes out there that are like 7100 Ultra, okay? So the 7 is still the strength, the next one is our position. And then naturally you have a T for tubular, okay? Totally tubular. Sorry, I like that. Totally tubular. X is the chemical composition, operating characteristics. I'm going to read a little bit from the book here, try to show you where it is. Okay, this last one also tells us whether it's dual shielded or self-shielded wire, okay, in a lot of ways. I find it here, we're on page 3-15, right-hand column, bottom. It says some electrodes are formulated, show you where, quick, sorry, right there. Some electrodes are formulated to be used without any additional shielding other than the contained within the electrode, aka at this point self-shielding electrodes, okay? They are designated by the suffixes 3, 4, 6, 7, 8, 10, 11, 13, and 14. So our last one, in our shop particularly, I've usually had to ask you, what does it end with, right? What are the last numbers in there? And there, in our shop, we run an 11, a Hobart, so it's E71T-11, right? T-1 is what we use for our gas shielding, so the next section. However, those electrodes having the numerical suffixes 1, 2, 5, 9, or 12 require some external shielding to aid in protecting the melting puddles, aka gas shielded, FCAW-G as well, versus S as self-shielded, okay? Or commonly referred to as a dual shielding process also. Now these will tell you also, the 11 will tell you it's a straight polarity machine. The 1 tells you it's a reverse polarity electrode, okay? Flux core electrodes are superior in their alloying capabilities for a couple different reasons. Fine granular patterns, small amounts, they don't require it to be in a large pool. So SMAW, again, it's a large electrode usually, a larger electrode, and you have to have more flux. So they require it to be dispersed at a liquid state to even out. Flux core, it's a small amount of wire, a small amount of metal, a small amount of flux, so it allows for a little bit more of a precision and accuracy, okay, instead of a larger piece. Stainless steel electrodes, same thing, they can be a flux core, right? So tubular, 308T, 308LT, low carbon versus that, same thing here. Yes, we can have a flux core stainless electrodes. We do it all the time in SMAW, okay? Gas shielding, flux core arc welding equipment, basically the same thing as GMAW, right? Just a different set. Now in this case the rollers might be, some people run them round, some people run knurled rollers. Typically you want knurled so that you don't smash, and you're also typically going to run a lower tension on your flux core tubular wires than you would on your solid core, okay? So if you're switching electrodes out, back the tension off some so you don't smash that in the middle and start cracking it as well. Self-shielding, same thing, except for now we don't have the gas source, right? Gas source here, no gas source here. Advantages, high productivity, deep penetration, tolerates contaminants, great fusion, suitable for field work within certain limitations. I mean, you don't want that good old 60-mile-an-hour wind to come through here, but a lot of times even in that situation, you can build a hooch around it, a hutch, to keep some of that atmospheric air off. You may turn your gas up a little bit, 35, 40, when you're outside with a little bit of a cross breeze, versus in the shop you may want to run 20, 25, to where you don't have a lot of cross breeze in there, okay? Some of the limitations, it still has a slag removal, smoky process, so forth, but I mean, you can weld a ton of iron with this. Any of you that have done it, I mean, you can lay down some serious welds, a very high deposition rate, good fusion. It's not going to look as pretty as some of your 7018 welds. However, for some people, it looks a little bit better than other people, right? I've seen some ugly 7018 welds in my life too, all right? Discontinuity, slag inclusions, porosity, you know, typically the same thing as everything else, but it also now we can get slag inclusions in there as well, okay? Typically gas shielded is all going to be done in a vertical uphill progression. Self-shielded, you'd want to come downhill. All right, GTAW. It almost seems to be almost everybody's wanting to take a break at this point.